We're told if f is differentiable at a, at a constant number called a, where a is more than 0, evaluate the following limit in terms of f prime at a. So what f prime at a means is the derivative of our function f at the constant a. We take the derivative and we plug in this constant a. Alright, so we have a limit here and we have to evaluate it. Well, the first step you should always take to evaluate a limit is see if you get anything out of just plugging in a. So let's do that really quick and see what we get. Do we get anything? Do we get a defined number? So we've got the limit as x approaches a. I'll just copy it down first. We've got inside, we've got f of x minus f of a all over square root of x minus the square root of a. So we are going to plug in x equals a. So we get, if we plug in x equals a, if we plug in x equals a here, we get f of a. So we have in our numerator f of a minus the f of a that we already had in the given limit expression. In our denominator, if we put a in for x here, we get square root of a minus square root of a. Well, we have something minus that same something divided by something else minus that same something else. What is this just equal to? Well, of course, this is 0 over 0. Does that mean our limit doesn't exist? That is just like nonsensical? Well, no. This is what we call indeterminate form. 0 over 0 is indeterminate form. So what does that mean? That means that this limit probably exists and we can find it. We just have to use some other method. We can't just plug in x equals a, as we've seen. So one way we can solve this is to use a very fancy sounding rule, but it's really quite simple to use. It's called L'Hopital's rule. It was made by a Frenchman named L'Hopital. L'Hopital's rule, and this is what the rule tells us. So if we have a limit as x approaches some number, it can be any number, I'll call it c, and our limit, if it is f of x divided by g of x, and f of x and g of x are really just any expressions that include the variable x. If this thing, right, if f of c, if we plug in c for x here, just like how we plugged in a for x over here, if f of c divided by g of c is equal to 0 over 0, or infinity over infinity, which is also indeterminate form, by the way, then we can say that this limit is equal to the limit as x approaches the same constant, except in our limit expression this time, we have f prime of x divided by g prime of x. So all we did, we took the derivative of, we plugged in c for x first, and we have to confirm that it's 0 over 0, infinity or over infinity. It can't be something like a constant over infinity. We can't use L'Hopital's rule for that. But if it's 0 over 0, just like how we got over here, so this condition checks out, we can say that this limit that we've been given is equal to the limit of the derivative of the numerator divided by the derivative of the denominator. And that helps us because now maybe we don't get 0 over 0. So let's try that out. Let's take this fraction here and take the derivative of the numerator and of the denominator. So using L'Hopital's rule, we got 0 over 0. So we can say that this is equal to the limit as x approaches a, and now we have to take the derivative of the numerator and of the denominator. So let's look at each part by itself. So what's d over dx of, and I'll do it in blue, f of x minus f of a. Oh. Well, f of x is a constant. Sorry, f of a is a constant, right? So if we take the derivative of this, the derivative of any constant, the derivative of any constant is 0. And remember, when we're taking the derivative, we can take the derivative of each added part by itself. So we can take d over dx, f of x and simply add that. Well, we have a negative out here, so we have to keep the negative there. We can simply subtract the derivative of f of a. Well, the derivative of f of a, because we're plugging in a constant, we will get a constant out of f of x. So f of a is simply a constant, and the derivative of this constant is 0. So really, we have the derivative of f of x minus 0. The derivative of f of x minus 0. So what's another way? So we have d over dx of f of x. So what's another way we can denote this? We're really saying the same thing, but we can call this f prime of x. These two expressions, they're the same thing. They're saying the same thing. Why am I putting f prime of x here? Well, that's what they ask us to put it in. They're asking to put the limit in terms of f prime of a. We'll get to the a part later, but they want us to use the prime symbol. All right, so we have the derivative of our numerator. It is none other than f prime of x. So let's look at our denominator. Our denominator is slightly more complex, but we can do it. So in our denominator, we've got d over dx of square root of x minus the square root of a. So what I want you to notice about this, it's very similar to the numerator. We can separate these two terms because they're being subtracted. We can take the derivative of each part and just subtract square root of a, the derivative of square root of a from derivative of square root of x. So this is equal to d over dx of the square root of x minus, because we have to keep this minus out here, or you can keep the minus inside the brackets as well. It doesn't really matter for us in this case. Why doesn't it matter? Well, we know that a is a constant, right? So if you take the square root of a constant, and multiply it by -1, you will still get a constant, right? If you take the square root of any constant, you'll of course just get a constant. Multiply that constant by -1, -1 is a constant, you will still get a constant. So what's the derivative of negative square root of a? That's just 0. So really, this is equal to d over dx of the square root of x. Notice, we are taking d over dx, right? So we have to actually take the derivative of the square root of x. So the square root of x, we'll have to use the power rule. Well, the square root of x is really x to the power of 1/2. So if we use our power rule here, and I'll remind you what it is, the power rule says that if we have x to the n, and we take the derivative of it, that is just equal to n times x to the n minus 1. So let's do that. Let's bring this 1/2 to the front and subtract 1 from this 1/2. So this is equal to 1/2 times x to the 1/2 minus 1. What is 1/2 minus 1? Well, you can think of it as 1/2 minus 2 over 2. Look at the numerators, 1 minus 2 is -1. So what's 1/2 minus 2 over 2? It is simply -1/2. So I just did 1/2 minus 1, and 1 is the same thing as 2 over 2. Alright, this would be a lot more useful if we put this into the fraction form. How do we put it into the fraction form? Well, this negative tells us that x to the 1/2 belongs in the denominator. So really, what we have here is 1/2 times 1 over x to the 1/2, and that is of course just equal to 1 over 2, and I can make this x to the 1/2 a square root again, just because it's easier to write that way. So the derivative of the square root of x is 1 over 2 times the square root of x. This is actually a good one to remember, because square root of x, that's a common thing to take the derivative of. Alright, so derivative of our denominator is 1 over 2 times the square root of x. Let's write that. So 1 over 2 times the square root of x. So how do we simplify this? Well, when you're dividing by a fraction, what you're really doing is multiplying by the reciprocal of this fraction, right? So we're going to multiply f prime of x by the reciprocal of this. So we still have to keep our limit out here because we have not founded the limit yet. We have to keep the notation. Square brackets. So what we have is f prime of x times the reciprocal of this. Well, if you take the reciprocal, you get 1 in the denominator, and in the numerator, you get 2 times the square root of x. Alright, so I'll write this without the dots in between. All right, so whenever you've put your limit into a new form, it's always a good idea to plug your what x approaches back in to see if you can get a constant now, or like a defined number. So let's do that. Let's, again, plug in x equals a. So if you plug in x equals a, we're going to put a right here for the x in our f prime. We'll get f prime of a times 2. Our 2 is just a constant, we don't do anything to it. And if we put a for our x here, we get the square root of a. Now, is this what they were asking for us and doesn't make sense? Well, we know that a is more than 0, so the square root of a definitely makes sense. You can take the square root of any positive number. And they asked us for the answer in terms of f prime of a, so f prime of a is definitely something that is defined, because that's what they asked us to put it in terms of. So really, this is our answer. This is the limit of x as x approaches a of f of x minus f of a all over the square root of x minus the square root of a. There's nothing else we can do with this because we don't know what f of x is. But this is what we were meant to find. F prime of a times 2 times the square root of a. That is the value of our limit.